Thank you very much. First of all, thanks to the organizers for a very kind invitation. Very pleased to spend a month here as a part of the thematic program. So I guess we're going to hear some mathematical talks today, right? So this is a mathematical talk. But there is more connection to what's going on here than the eye can meet, maybe. So the sort of the name of the game here is collective dynamics. Okay, so the models that we study, they kind of originate themselves in a different subjects, behavioral biology, things like that, emergence, some technological applications. But the tools that we use to study these problems, they can be quite universal, right? I mean, again, transferable to other subjects, and in particular the alignment dynamics, things like synchronization of directors, things like that, that may appear in electrochemistry in particular, may be useful. So my goal is going to be to sort of spend a lot of time on motivation, okay, and why we study what we do, because usually this well-posedness talks may be quite technical and boring, so you have to really motivate why you need regularity of these questions, and what we can do with that regularity, okay? So so these are examples of collective behavior that we study in biology. There's social studies, opinion dynamics, things like that. So there's a very nice application of this what we call three-zone model, which is just basically a model of very primitive but effective model of communication between birds, which Craig Reynolds, this guy here, used to encode into early computer simulations of flights of birds, and they were actually implemented in movie production, okay? So we're here in Hollywood, and you don't see every day a scientist getting not a Fields Medal, not a Nobel, but Oscar. Okay. He got an Oscar for this contribution. So this is very, very nice. He produced really realistic flights of birds using this three-zone model, which includes basic repulsion and attraction potential, and also alignment, which is important, right? So we're gonna talk about this middle region a lot. So basically, we start with agent-based models. Okay, these are not first principles as in physics. These are phenomenological models, but they encode some kind of interactions between agents. We call them agents, not birds, because they could be opinions, for example, right? So and what we study is formation of patterns. So this is kind of, oops, does it work? Okay. We have this cumulative term for it called emergence, right? So emergence is the appearance of global patterns out of only local interactions, okay? So there are local rules that result in some kind of global formation over time. So usually you can see some disordered state first, then you have some local organization, and then results over time in global organization. So the prototypical and very classical model for alignment dynamics is Cucker-Smale model. So it incorporates basic communication between agents xi, xj through some smooth radially symmetric and decaying kernel. Basically sort of like encodes the weighted averaging of communication and how the velocity vi aligns to velocity vj, okay? So naturally to expect that the farther the agents are apart, the weaker communication is, right? And so this model actually appeared as a response to other models that, of course, there were many other models in the literature, but that kind of gave a very good mathematical criterion for long-time dynamics, okay? Just using some information about the kernel and not using anything about the connectivity of the flock and things like that. So one of the things that you can see is that the model is symmetric with respect to agents, And so as a consequence, you have a conservation of momentum. And you also have a nice energy law, which dissipates energy as long as the agents are not aligned. Okay? So as long as you have some disorder, there will be energy burning until you set at some, hopefully aligned state. But of course, the problem is that if this kernel is local, speaking about emergence, right, you have only local rules of interactions, you may see formation of clusters, right? There's some cluster aligned here, some cluster aligned there. They never communicate, so they can just live alone without any bothering each other, right? So the threshold when this cannot happen was actually found by Cucker-Smale in the original paper. So this kernel has to have a long tail, right? It has to have a heavy tail, what we call, which is non-integrable at infinity, okay? And this is actually a criterion. If it is integrable at infinity, even if it's long, you can actually find a counterexample to alignment. But it does have fat tail. Then you have a flogging, so the flog remains bounded, actually crystallizes to kind of over time to a fixed graph, and there's exponential alignment between velocities. Okay, so in this particular formulation, this actually was proved by Hao and Liu. And just to disambiguate, Liu is our first speaker. So it's a classical paper, maybe disconnected to what he was talking about today, but this is really a classical paper where they also proved mean field limit. So speaking of which, we always pass to sort of statistical description of the flux if the number of agents grows large. This was formally derived by Ha and Liu in 2008, and then, sorry, Ha and Tadmer, and then Liu justified it through basically the Bruchian stability theorem. For smooth communication kernels, for singular, it remains an open problem. And you arrive at this kind of interesting Vlasov alignment model, which kind of looks like, gas dynamics equations, but these are not collisional models. Okay, so they're really mean field models. And the study of long-time behavior of this model is very similar to discrete system because you just study them along the characteristics. It's a transport equation, and you can arrive at the same conclusion as in the discrete system. Now, you can justify macroscopic system using various regimes. So one of the first regimes was monokinetic. When you enforce this system, we put a very strong local alignment force. And in that case, the distribution converges to the monokinetic ansatz. This was proved by Figali and Khan 2019 with no vacuum condition, and then we removed vacuum condition a year later. So this pressureless Euler alignment system has been the subject of a lot of studies recently. Okay, it's a very interesting system to look at from the hydrodynamic point of view. It's a compressible system. It has two fighting effects. One is Berger, blow up. Basically, the equation wants to form shock, as any compressible system, of course. But this Cucker-Smale sort of alignment part plays a regularization effect, especially if the kernel has singularity at the origin. Like, for example, Coulomb, or even stronger, like fractional Laplacian, you have a mixture of transport and dissipation. They fight each other in terms of regularity and see who wins. So there's a whole theory about it. In 1D, we understand it very well. In multi-D, we basically understand nothing. So I'm going to be using this notation here, rho sub phi, to denote the convolution with the kernel. Okay. So you can also justify stochastic, speaking about stochasticity. But the way you introduce noise is very, very important. It has a huge implications on long-time behavior for your kinetic system. So the way we choose to introduce the stochasticity here is to be sort of in a multiplicative way. So we want the strengths, strengths of the noise to be comparable to the total communication range of the agent, right? Beyond the communication range, there's no point to introduce the noise. You're like putting noise in the vacuum, right? You want to put the noise where the interactions are. And so this is the motivation for this. And you can justify the limit under certain mathematical assumptions on the distribution, and you arrive at the Fokker-Planck, what we call Fokker-Planck-Alignment system, right? So it has this still sort of a deterministic alignment part, and the effect of the noise comes in terms of Laplacian in V only, right? And also with this coefficient, which is convolution of density and the communication kernel. So the complexity of this comes in two ways. One is that you have diffusion only in the V on the kinetic direction, which is not really a fully diffusive equation, right? But we know that together with the free transport, it creates a hypoelliptic structure. So there's good regularity that comes with it. But the main problem actually is that this coefficient here can vanish, right? Beyond the range of communication of the flock, especially for local kernels, this coefficient can vanish, and you sort of have like a mixture of transport, transport and also diffusion where the flock is. So the flock diffuses where it is, but it doesn't where it's not present. And so studying this regularity of the system, it becomes a very, very challenging problem for this reason, okay? You can pass to the Maxwellian limit now from the Fokker-Planck, and you obtain what we call isothermal Euler alignment system. So that's a sort of noisy analog of the pressureless system. Okay, so the same theorem that holds for discrete system about long time behavior under fat tail kernel holds also for kinetic and for hydrodynamic models. And the models has seen a lot of applications, in particular to satellite navigation. For example, these engineers here, they calibrated the particular value of beta coefficient to be 0.4 to be the most energy efficient for satellites to fly and synchronize themselves to burn less fuel, and yes, to synchronize to a point that they can sort of take pictures of planets and things like that. So people use it in control problems. Machine learning techniques have been used to learn fractional kernels, singular kernels. And that's a whole separate subject. We're going to be focusing mostly on smooth kernels here. And also, of course, to place the alignment dynamics inside those two-zone or three-zone models that I mentioned with regard to Reynolds' work has been basically underdeveloped at this point. Okay, we only know two-zone results. Three-zone results are extremely difficult to understand, partly because there are no natural steady states, okay, or even periodic solutions in the limiting dynamics of this problem. So it's very hard, but some progress has been made here. Okay, so Cucker-Smale is just sort of one of a whole zoo of models that people introduce. And the reason why people introduce those models is because Cucker-Smale doesn't work well in some heterogeneous flocks. So for example, if you have a tiny flock which is remote from a big flock over here, the dynamics of the big flock can hijack the dynamics of the small flock, which is not a realistic behavior. So basically what's happening is that these little birds here will fly like as if they don't interact with each other at all, because their weight of communication coming from the large flock suppresses any forces between them. So let me just show you a short movie to illustrate the point. This was done actually by my student, former student, Trevor Teolis. Okay, so this is the dynamics under, okay. These red dots is the heavy, despite the fact that there are only 3 of them, but this is actually a very heavy flock, okay? And the green ones there are many of them, but they're very, very light. So this is a small flock. So what you're gonna see is that the big flock aligns pretty fast. I mean, it's kind of aligning. And the green flock, they disperse without, like as if there's no forces between them acting, right? So Moch and Tadmor introduced this renormalization trick where you basically take the total sum of all interactions and you divide by it, right? So it kind of recalibrates the internal forces inside each subflock and making them more natural. So if you look at the dynamics of the same initial condition under Moch-Stadmer protocol, you see that the green flock starts to align in a more natural way. Okay, so in this kind of situations, you have to depart from the classical Cucker-Smale and use some other renormalized models like this. Now, unfortunately, the analysis of these models becomes tricky because the kernel is not symmetric anymore, and there's no conservation of momentum. So the momentum kind of emerges as a dynamical quantity over time and no energy dissipation. But Cucker-Smale theorem still holds because Cucker-Smale theorem is not based on the energy. It's based on L infinity. It's a maximum principal result. OK, so if you put them in hydrodynamic notation, then you can see the difference between these two models. There's a weight here, communication strength for Cucker-Smale. There is no weight here. You can, in principle, interpolate between them and look at a whole range of what we call beta models. To restore the symmetry in Moch-Stadmer, you can put another convolution with communication kernel. Okay, and this actually brings a lot connection with machine learning. Okay, I will mention this a little bit later in terms of computation of spectral gaps. And segregation model, for example, when you have neighborhoods and people try to communicate within each neighborhood, and we study alignment sort of localized within each neighborhood and study what's the what's the consensus of this process. So all these models introduce certain averaging operations. Okay, this is, by the way, called the Favre averaging. Somebody who does simulation of non-homogeneous turbulence knows what that is. Multi-species, multi-flux topological models. There's a whole range of interesting models. They can kind of can be studied in a general framework, which we've sort of described in this monograph. Basically, what you have at hand is an averaging operator, the strengths of communication, and there's a communication kernel. Okay, nothing new over what I already said in the Cucker-Smale case, but in this general framework can encode all kinds of nuances that you put in your communication protocol. Moch-Stadmer, interpolated, topological, all of this. Okay, and these are sort of examples of the kernels that you can read off from the models that I just quoted. Just looking at these kernels, I mean, you can clearly see that some of them are symmetric over here, or this one, and some of them are not, like Moch-Stadmer. So all these properties of the kernels, they bear direct consequences to the dynamics of the corresponding differential model they're implemented in. OK, so let's go back to this emergence problem. Suppose that you have local communication only. What can we say? Okay, if you're in the open space, you can easily cook up two flocks just flying away from each other, right, without ever communicating. So this is kind of a trivial counterexample we want to avoid. One way to avoid it is to put some kind of confinement force, for example. This makes the model a little bit more complicated in the open space. Or just for mathematical simplicity, let's consider periodic domain. Okay, it can be any compact manifold for that reason, but torus is flat, so you don't have any curvature to deal with. So let's just look at torus. So in that case, you still have these very rare flock configurations where the agents don't communicate. So for example, you can move one agent along one geodesic and the other agent along another geodesic. If their velocities are mutually rational, you can arrange them in such a way that they don't even interact, right? They don't come close. They never collide, right? So, so we call them locked states, right? Because they kind of go in this periodic way all the time. And they're also very, very rare. They actually form measure zero set in a state space, right? So if you assume that there's some kind of connectivity of the flock perpetual for all time, then you can avoid these locked states, okay? But generally, we have this conjecture we call generic alignment conjecture, which says that for almost every initial data, the flocks should align, okay? So we should be able to avoid this kind of states almost everywhere. This is actually very simple stated conjecture, and it's open, okay? We cannot solve it. unless you have some very specific cases. For example, for the sticky particle model, we can do that using chronic characterization of subtori. Or you can prove it for 2 agents. Okay. Actually, you can prove this for any number of agents, but only partially. For a system of any size, at least 2 agents will align, generically. Okay? So it's kind of a statistical argument using Poincare recurrence theorem. Okay? Agents come back, come back, come back. Some of them will communicate all the time. When they communicate, they have to align. But for 3 agents, we don't know already. So it's a dynamical system problem, maybe not a PDE problem. So I'm not going to stay too much on that. What I'm going to focus on is this noise. Okay? When you introduce a tiny noise, it definitely disrupts these locked states, right? And when it does, we have hope to prove long-time behavior, even for local communication kernel. Okay? And that program has seen partial success. Okay? So basically, what we're trying to establish here is that let's look at our stochastic ODE. We arrive at the corresponding Fokker-Planck-Alignment equation, which I described already before. And the long-time behavior becomes the relaxation problem. Okay? Now, the reason why we introduced that noise, special noise in front of the special coefficient in front of the noise is because that way the equation has a natural steady state, the Maxwellian equilibrium. And so you have a chance to prove that any distribution will relax to that Maxwellian. Okay. If it does, then we can understand the alignment in the sort of vanishing viscosity limit, vanishing noise limit, because Maxwellians will concentrate to Dirac, of course, when you let the sigma go to 0. So sort of kind of bringing us analogy with turbulence problems in fluids, right? We always understand statistical laws of turbulence in exactly the same way. You first take small viscosity, let time go to infinity, let the solution settle on the attractor, which in this case is just simple global Maxwellian. And then you read off statistical laws of turbulence in the vanishing viscosity limit, okay? Then you will see the Kolmogorov laws and things like that, energy dissipation rates. So here is sort of similar philosophy, but much simpler in the sense what you will expect in the end. What you expect is alignment. So, so as I said, this program has started in 2010, had a partial success. So the first results were perturbative. If you consider, so let's say in the Cucker-Smale case, Duan, Fornazier, Toscani looked at perturbative data around the equilibrium. And perturbation has to be very, very small and high order weighted Sobolev spaces. Then you do converge exponentially fast. So it's basically a stability problem of Maxwellian. Yeah?
Is the noise term the same as you had before? Or
yes, it's the same. Yeah. It's a particular Cucker-Smale case. So the noise is just a convolution of density with the communication. Okay? Now, you can consider local alignment. Okay? Just V minus U is a macroscopic velocity with simple communication, with simple coefficient. Thermalization, sigma is constant. So Choi has done it in 2016. And the same works as before. The challenge here is that this macroscopic velocity is rough. So you have to overcome this problem of, it's unbounded and rough macroscopic velocity, but still perturbation technique works. It's kind of motivated by techniques that appeared at the time from collisional models like Landau and Boltzmann. So the first global result for large data was established for this Moch-Tadmor symmetrized model. Okay, so here the issue is still because you divide by rho phi, this can be quite singular, but at least you don't have the problem with the degeneracy of the noise. So, but you need to assume that macroscopic velocity is uniformly bounded for all time. So if you have a solution with observable macroscopic velocity under control, then it will relax exponentially fast. Okay, and I was quite happy about this at the time because, if you look at the collisional results like for Boltzmann or Landau, they always rely on some kind of macroscopic assumptions, right? So, OK, great. But turns out that you can do better. So let me sort of go back to this Cucker-Smale, the original model, OK, and state a few results. So here's one. Suppose that the kernel is what we call Bochner positive. OK, it has like a convolution square root. So it's a convolution of another positive, smooth, nice kernel with itself. Is it a restriction? Yes, it is a restriction. OK, it makes the averaging, the corresponding averaging positive semi-definite, OK, which is what we use in this results. But for example, if you want to model local kernel, you can assume that psi itself is local with radius half of what you need. Then the convolution is going to just be of the radius that you need, right? Because the supports of the convolution adds up algebraically. So it's not really that much of a restriction. I mean, draw a bump, and I can tell you that it's probably like that. So then what's happening is the following. You have a spread of positivity instantaneously, okay? Despite the fact that this is a degenerate noise, you spread positivity instantaneously. In fact, the distribution f itself will gain Gaussian tails. It will try to mimic the form of the corresponding Green's function, okay? And what's important here is that it will remain so uniformly for all time, okay? So all this spread of positivity results that we know for Boltzmann equation of Landau, they fluctuate in time. They can actually go to, I mean, they depend on time. They can go to 0. Their size, no vacuum condition, kind of depends on the regularity of solution itself, which can deteriorate, of course. But in this case, we've got this uniformly in time, and consequently, because of something that I will say later, you will have exponential relaxation. Okay. Now, exponential relaxation holds with these particular rates, sigma to the power 1/2. Of course, they will deteriorate when sigma goes to 0. But the point is that we first let time go to infinity, and then we'll let sigma go to 0. Okay. We first let settle on the attractor, and then we let noise go to 0. So it's not really that much of a philosophical problem, but it does vanish, of course. Is it an optimal rate? Maybe 1/3 is more optimal given the enhanced dissipation technique. We haven't used that. This is what comes out from hypercoercivity. So, so to prove that, you need to work with, OK, so this brings me to why we need regularity of the solutions, right? To prove this result, you need to put a lot of derivatives on your solution, OK? So you need to know that your solution is regular, so you can make these calculations not formal, but rigorously. In particular, you need to know the Fisher you need to know the finiteness of Fisher information, things like that. So the ingredients are the following. I already basically said all of that. You gain Gaussian tails. You need to compute spectral gap of your averaging operator. And this is where sort of the techniques that are parallel to machine learning. I'm learning now. What we've been doing here is basically machine learning. Allows us to compute the spectral gap of the average in terms of lower support on the density, okay? So once we know Gaussian tails, uniform no vacuum condition, this results in uniform positivity of the spectral gap. And that is a prerequisite for relaxation. And then we run Villani-type hypercoercivity arguments a la Bakri-Emery method basically applied to the alignment models. So these are 3 sort of big chunks in this proof. So just to give a few details, so we use this Villani framework of dissipation drift formulation of Fokker-Planck equation. It applies very well for the classical Fokker-Planck. In fact, he's written this book, Hypercoercivity, published in Memoirs, where he laid out a very general scheme where you can apply this for many, many models, in particular for Boltzmann equation. But unfortunately, the reason why it doesn't apply to us is because exactly of this alignment term. The alignment term does not fit into that hypercoercivity framework, so you have to do something, right, to make it work. And what happens is that you still have the entropy. Okay? So it's like a Boltzmann entropy, which we sometimes called relative entropy, in fact, because it measures distance between F and the Maxwellian. And it actually has two forms. So one is discouraging form, because if you look at this entropy law, it has the classical Fisher information, but it also has this residual alignment energy, which basically tells you you've been too ambitious. Okay, you're trying to push yourself straight to the global Maxwellian without disregard to any effect from the alignment. And this is the price you have to pay for it. Okay, this can be actually positive. So the Fisher is pushing you towards Maxwellian, but the alignment is pushing you away from it. And in fact, this is actually kind of what happened in the Boltzmann equation. It goes back and forth until it settles to this manifold. So, but for us, there's also another form of the Boltzmann equation. Of the entropy law. You can sort of rearrange terms, trade between now not just Fisher information that measures distance towards global Maxwellian, but instead towards local Maxwellian. So you're kind of giving yourself some slack. You're less ambitious, but that creates a sign definite law. Okay, and so at least the entropy is under control. So this is the spectral gap that I was talking about. So it's basically the second eigenvalue of the averaging operator, the Favre filtration, and this is the very important inequality that kind of makes everything work. So the spectral gap is actually proportional to the cube of the infimum of the density. So you can actually prove these results for other positive definite models. For example, over mollified symmetrized Moch-Stadmer that I mentioned, or for segregation models. And we've been doing this for each model separately, and it looked like very ad hoc. So every time you have to invent something, how to compute it. But it turns out that what we've been doing is what people in machine learning have been doing. It's what's called the support vector machines, the kernel trick, right? So you introduce what's called the feature space or feature transformation. So your positive definite kernel can be written as the inner product of some feature transform over some abstract Hilbert space, okay? And people use it in machine learning to actually simplify the feature space. I mean, every objective may have a lot of features which you don't care about. All you want is to compare how similar two objectives are. So you want to forget about this feature space and instead look at the kernel, okay? Like look how far they are from each other. We're actually doing the other way around. Kernel we know, okay? And for us it looks mysterious, but once you look at the features, which is basically all the communication neighborhoods our agent is involved in, then I can compute spectral gap using the particular nature of that feature space, okay? So we're kind of doing it the other way around here. But technique is very, very similar. I mean, setup is at least very, very similar. Of course, for us, everything depends on the density here, and the feature space depends on the density. So there are some other additional mathematical structure that comes into it. So anyway, this is one of the spectral gap results that we can prove, particularly for the Cucker-Smale model. And so what this happens is that now this guy here is proportional to the negative full energy, okay? And I can combine this law of my entropy law with the previous one to kill this residual energy, okay? So once I've done that, we run the Bakri-Emery method, like in the classical Villani sort of framework. But again, things don't go that smoothly. Okay, things need to cancel. The alignment term always appear in all these computation of the Fisher information equations. Things need to cancel and be under control to make this work. The point is that we need a lot of regularity of the solution in order to make this work. And you will, if you do have that, you will arrive at some Lyapunov function. And by Caesar-Pullback inequality, it controls the L1 norm between your distribution and the Maxwellian, okay? So I'm not going to stop anymore about there's a spread of positivity results, a very classical result, and for us, what's important is that it's time independent. We study the regularity in higher order weighted, cooked up, especially cooked up weighted Sobolev spaces. Okay, and let me just say that in principle you can obtain some solutions. Okay, so for example, through the stochastic mean field limit, under very, very stringent assumption on distribution, it has to be sub-Maxwellian. Okay, this is not really what we want because it kind of is very close to perturbative results if you work with these assumptions. The closest result to us was actually proved by Karper-Mellet-Trivisa in 2013 under just finite energy. Okay, and that's the settings we want to work with. But these are just weak solutions. Okay, there's nothing else that has been known. We have very rough solution that propagates for all time. We need more regularity. So to get more regularity, we start with thick flocks, flocks which have mass in communication balls all over the environment. So in that case, you can prove local wellposedness, and in some case, global wellposedness, depending on the properties of the averaging itself. But it does work for Cucker-Smale model, for example. So for Cucker-Smale model, the averaging operator is regularizing. It's just a convolution of the momentum with communication kernel. Okay, so this is what it is. And so of course, it belongs to C infinity even from any finite energy macroscopic momentum. So in that case, you will get global wellposedness in these weighted Sobolev spaces. So the result is that you can start with weak solution, okay, just like in Karper-Mellet-Trivisa. With you're going to get a weak solution with finite Fisher information, but this coefficient can be degenerate, so we have to deal with this difficulty because we don't have access to this Fisher information in a direct way. And what's important is that we have first ingredient for the hypercursivity is the entropy equality. Okay, so you do have the entropy law that actually comes as a consequence of de Perna-Lyon renormalization. So every weak solution can be shown to be renormalized. So you can basically compose your solution with any other nice function, and you get corresponding equation. So the entropy law the proof of the entropy law is very similar to the proof of Onsager conjecture. So this is kind of has very nice connection with what has been going on in incompressible fluids over the last 10, 20 years. The critical regularity threshold for energy conservation for incompressible Euler equation has been known since Onsager 1949 paper, which is Herder 1/3. Okay, it's motivated by laws of turbulence. Has been proved only recently, okay, using convex integration technique. So for Fokker-Planck equation, the corresponding threshold is actually Fisher information, which is available, okay, if it's not degenerate. It is, however, degenerate. And so to access this regularity through the degenerate weight requires renormalizing the equation in a special way, okay, using communication strength weight. And once you've done this, it results in sort of a huge system. You kind of feel that you want to give up and maybe do another problem. But if you persevere, you'll see that, all these little terms, all these energy fluxes, they vanish as epsilon goes to 0 and approximation parameter goes to 0, and you arrive at renormalization. So at the end of the day, you get your favorite entropy law. Now, what else can we say? Fokker-Planck equation solutions tend to regularize, right? So there's this global hyperellipticity effect, but this effect only holds if you have a non-degenerate diffusion, because that's coming from the diffusion. So the only assumption that we have to make is the same as I already written before. Once the averaging is a little bit regularizing, then everything regularizes straight into C infinity, okay? you start with a solution with high momentum, but there's no regularity assumption made. You instantaneously become regular. Once you become regular, you can do the long time behavior analysis. Okay? All you need is, you don't even need any nice bounds on these higher derivatives. All you want is just to differentiate your solution. So this is the sort of my last slide, the summary of these results specifically for the Cucker-Smale system. Okay? So what do we have? This is the only assumption you need to make. Your kernel is Bochner positive. Okay? Then, for any initial data in the rough space with high momentum, the momentum will propagate. The Fisher information, although degenerate, will be positive. But this degeneracy will go away instantaneously because you gain Gaussian tails, and it will remain so uniformly in time. The solution will become C infinity right away, and it will relax to the Maxwellian with the rates that I already mentioned. Okay. So this is basically a full answer in the case of Cucker-Smale. Now, I mentioned a lot of other models, like Moch-Stadmer, average Moch-Stadmer. For them, we don't know that full result. We know ingredients of it. For example, we know perturbative results for all those models. We know that if you're sort of halfway between Cucker-Smale and Moch-Stadmer, you get regularization, but you don't have uniform spread of positivity, so therefore we cannot quite conclude the same asymptotic result. So this remains an open problem here. So, the tools are hypercursivity and spread of positivity, so using big Harnack inequalities, things like that. So I'm pretty sure that in a lot of models that already appeared here, things like synchronization, alignment of these crystals or things like that will appear. And we may talk about whether this technique would be applicable in that case. So thank you for your attention.